Hello, everyone. Here we go with lesson 3. It's very similar to lesson 2, which was we were given that a quadrilateral was a parallelogram. We were given a parallelogram, and then we were concluding certain things about the angles, sides, diagonals, and all that. You should remember those properties. Today, we are going to be doing the converse, or the opposite. We are going to be given a characteristic, and we need to determine whether that information is enough to say we have a parallelogram. So there's a few theorems that go with this. I'm only going to prove one of them, but then we will look at the other ones. So go ahead and get it set up here. Theorem number 1 for today is that if the diagonals of a quadrilateral if the diagonals of a quadrilateral, notice it's not a parallelogram because we're trying to prove that it's a parallelogram. If the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. So we can say that it is a parallelogram. All right. So in this picture here, I'm giving you that AC and BD bisect each other. What we want to prove is that ABCD is a parallelogram. And I'm going to shorthand this. Right? You know what I'm saying there. In other words, we need to show that both pairs of opposite sides are, what's the definition of a parallelogram? That they are parallel. How do we show that two things are parallel? We look at their, well, we'll get back to that. So let's look at the proof. Stretch this out here. All right, it's a long proof, so bear with me. So first thing is AC and BD bisect each other. That's given. Well, what does that mean? Well, it's kind of already shown on the picture, but AE equals CE and BE equals DE. That's what bisect means. So definition of bisect. All right, well, then I'm going to go one more step here. Oh, not one more step, but angle AED is equal to angle CEB. Those are vertical angles if you look at those. So vertical angles theorem. Okay, I'm going to mark these things down real quick. Well, actually, just that piece right there. AED is that angle. CEB is that angle. Those are vertical angles, which is enough to say that triangle AED equals triangle CEB. That's side angle side. Well, if the triangles are congruent, I could then say that angle EAD is equal to angle ECB by CPCTC. Now, why those angles? I'll show you those angles real quick. I'm going to change colors here. EAD is this angle, and ECB is this angle. Why those? Well, those are alternate interior angles. And if alternate interior angles are congruent, I can say that the two lines are parallel that make those alternate interior angles. So I can say AD is parallel to BC by the converse of alternate interior angles theorem. Well, I'm going to shorthand that up. All right. Now that's only one set of parallel lines. I need both sets. Well, the next few parts are actually pretty easy. They go a little, it's basically the exact same proof from step 3 down to step 6. So instead of the triangle on the left and the triangle on the right, I'm going to look at this triangle and this triangle. That's what I'm going to do. So angle AEB is congruent to angle CED. Again, vertical angles theorem. Then I can say that the two triangles are congruent. By side angle side. Then I can say angle EAB is congruent to angle ECD by CPCTC. And then I can say AB parallel to CD. And that's converse of alternate interior angles theorem. Now that's almost the last step. The last step is what I am trying to prove. Because opposite sides are both parallel, I can say ABCD is parallelogram. That's the definition of parallelogram. Okay, so a very long proof, probably the longest proof you've ever seen, 11 steps, but it shows you that because the diagonals bisected, I was able to go from step to step all the way down to show that it's a parallelogram and prove it. Okay. Next, from here on out, I'm not proving, I'm just going to draw what's going on. Okay. So theorem number 2. If one pair, and this one's a little bit weird, this one was not on lesson 2's notes. If one pair of opposite sides of a quadrilateral is both parallel and congruent, then the quadrilateral is a parallelogram. So draw a parallelogram that shows this theorem. All I need is one pair of sides parallel and congruent. Now, I will see people who think that this is a parallelogram. These are parallel and these are congruent. That's not a parallelogram. Okay. If both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. So what this looks like is, here's a parallelogram. What it's saying is the opposite sides are congruent on both. And if you have both of them congruent, it's a parallelogram. Okay. Theorem 4. If both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Okay. Try to draw this one. Try to pause it and draw it before I do. All right. So if I have a quadrilateral and this angle is equal to this angle, that alone is not enough. I need both pairs. So I need this congruent to this. And that would make a parallelogram. So that's the 4 theorems that prove that something's a parallelogram. Okay. The next few problems, the next example, actually, we've kind of done this already, where what values of X and Y would make this a parallelogram? Well, if it was to make it a parallelogram, I need the diagonals to bisect. So that means 2y minus 7 has to equal y plus 2. And you should get y equals 9 here. Oops, that's y. I'll switch colors. And then for x, I get x plus 5 equals 3x. I get 5 equals 2x. 5 divided by 2, or 2.5 for x. All right. The last few questions here. These are what you're going to see on your test. Is there enough information to prove the quadrilateral is a parallelogram, and explain? All right, so the first one, what is shown? That's what you have to determine. What is being shown? Well, I see those congruent sides. All 4 sides are congruent. Well, what does that make it? If all 4 sides are congruent, it's a rhombus, right? But isn't a rhombus also a parallelogram? All right, so if it's a rhombus, it's also a parallelogram. So the answer to this one is yes, it's enough. All rhombuses are parallelograms. You could also explain it with the fact that both pairs of opposite sides are congruent, right? This side is congruent to this side, and this side is congruent to this side. They just happen to be congruent to all each other. So, yeah, it's theorem number 3, but it's also showing that it's a rhombus. So there's a couple different ways to explain that. Next one, a lot of people think that it looks like one and that it is, but in fact, it is not. What this actually shows is an isosceles trapezoid. Look back at theorem 2 on the video. I showed you this exact picture. Maybe I swapped the parallel and the congruent, but the theorem number 2 says that the same side pair has to be both parallel and congruent. Okay, this one shows one pair parallel and the other pair congruent. That's not a parallelogram. Okay, third one. Looks like the diagonals bisect each other. And a lot of people think, yep, they do, but in fact, they do not. If they bisected each other, these two would be equal, and these two would be equal, but that's not what's shown. Okay, that's not enough. This does not show diagonals bisecting. Therefore, I cannot say it's a parallelogram. All right. Last one. Is this enough? Well, I've got the parallel and I've got this M. Well, if this is M and this is also M, aren't those congruent? So I got this is enough. Both, sorry, back it up here. One pair of sides is both. So one pair of sides is both parallel and congruent. All right. And so that is lesson 3 in a nutshell. I know I went pretty quick, but we'll practice it in class and hopefully we make sense of it.